Hello, my name is Michael Prerau, and I'd like to talk a little bit about a method that we've developed to track the way in which someone falls asleep. So how do we know when someone has fallen asleep, and what can we learn from the way in which someone has fallen asleep? These are important clinical questions for us to be able to answer in the case of disorders like insomnia, where it takes a longer time for someone to fall asleep, or disorders like hypersomnia and sleep deprivation, where people typically fall asleep much quicker than normal. These questions overall have not been really easy to answer, so we're trying to find new ways of addressing the problem. The sleep onset process, or SOP, refers to the gradual transition between wakefulness and sleep. Every scientific study thus far has shown the SOP to be a continuous, dynamic process where aspects of behavior and physiology gradually change, but often at different rates and in different directions. The current clinical standard for calculating sleep latency, or the time it takes you to fall asleep, involves estimating a single moment in time before which you are awake and after which you are asleep. Since this metric does not capture the continuum of the sleep onset process, estimates of sleep latency differ greatly depending on what measurements are chosen, with large differences between estimates based on behavioral tasks versus estimates based on physiological measurements. Additionally, by choosing only one time as the moment of sleep onset, this approach takes a collection of different continuously evolving observations and imposes an instantaneous transition model on the data. We are limited to a binary state where all the observations instantly transition from wake to sleep at the same point. This approach of defining a single moment of sleep onset imposes an unrealistic model of coincident, instantaneous transitions in all observations. As a result, current clinical methods simplify the sleep onset process in a way that severely limits the accuracy, power, and scope of any resulting clinical metrics. As early as the late 1930s, people have recognized the problem of trying to determine the moment of sleep. To paraphrase Davis et al., finding the exact moment of sleep onset is as difficult as finding the exact moment of death. In this video, we will discuss measuring the sleep onset process, the wake probability model, which is a model we developed to track the changes in sleep onset over time, characterizing the transition from wake to sleep using wake probability, and using wake probability to compare the sleep onset processes between different groups or populations. So how could we go about improving our ability to predict not only when someone has fallen asleep, but also the way in which they fall asleep? We want to create a method that treats sleep onset as a continuous and dynamic transition, allows observations to evolve on different timescales and at different rates, integrates information from both behavioral and physiological observations, intuits the subject's state based on the superposition of all of these observations, and is based on physiologically principled models. And, in addition to all of this, we want a method that uses a statistically principled methodological framework which allows us to look at things such as uncertainty, goodness of fit, and deal with missing or noisy data. In order to meet the criteria we have set out, we first need to improve the way in which we measure the sleep onset process. From a behavioral standpoint, there are two types of tasks that scientists have used in the past: active metrics and passive metrics. Passive metrics are recordings such as actigraphy or a dead man switch, which are good because they have minimal sleep disruption. However, these metrics rely on limited observations and also impose the false assumption that when you are not moving, you are asleep. Active metrics, such as auditory response tasks, which require someone to continuously respond to stimuli, can provide many observations, but the stimuli can also disturb sleep. Additionally, the subject can feel like they are pressured to perform the task, which could disturb sleep onset, and the extended technical setup required to perform and record the metrics could prove burdensome to experimentalists. Ideally, we want a behavioral metric that gives us the many observations that we would get from a behavioral task, so we're able to look at the continuum of sleep onset evolving over time, but at the same time provides minimal disruption to the sleep of the participant. Furthermore, we want a task that doesn't require a lot of technical setup and doesn't make the subject feel like they're compelled to complete a task, which could disturb the way in which they fall asleep. To achieve the aims of finding this ideal behavioral metric, we came up with a new technical setup and a new task in which the subject was given a squeeze ball. EMG sensors were placed on the muscle responsible for finger movement, and finger motion was further confirmed by mechanical sensors on a glove. The subject's breathing was tracked using standard clinical respiratory sensors like PTAF, airflow, and abdominal belts. As they were falling asleep, the subjects were asked to gently squeeze in the ball as they breathed in and to gently release the ball as they breathed out. They were asked to do this for as long as they could, and if the ball rolled away while they were falling asleep, let it be. The subject may not realize it, but they are in fact completing a behavioral task by doing this simple breathing exercise. As the subject breathes in and squeezes at the same time, we can compare the EMG of the muscles responsible for squeezing in the subject's respiration. If the breathing lines up with the muscle activity of the squeeze, we view this as a correct response, and if there is a breath without a squeeze, it is an incorrect response. Over the course of the sleep onset process, we can use this task to collect many observations just as in an active behavioral response task. Moreover, the actual squeeze force recorded by the EMG provides a lot of additional information. By recording the EMG activity at each breath, we can observe how the strength of the squeeze diminishes during the sleep onset process, as well as the underlying muscle tone after they have fallen asleep. This new breathing task therefore satisfies all of our criteria for an ideal behavioral metric. We are collecting many observations with no stimuli to disrupt sleep. There is minimal technical setup as it only requires a squeeze ball and a single EMG which can be integrated into standard clinical recording setups. And the subject doesn't feel like they're being pressured to perform a task. Moreover, there is significant literature indicating that repeated, focused breathing can produce many physiological changes that could facilitate sleep. Simultaneously with the behavioral and EMG data, we can also observe changes in brain activity by looking at the brain waves in the electroencephalogram, or EEG, and how their dynamics evolve over the sleep onset process. Here we have an EEG spectrogram of a subject during the sleep onset process, with the x-axis showing time, the y-axis showing frequency, and the color indicating power. To learn more about the sleep EEG multi-taper spectrogram, please visit some of the other modules and tutorials we have on our website, sleepeeg.org. In the spectrogram, as the subject falls asleep, we have a strong alpha power that disappears and gives way to an increasing rise of delta and theta power. If we view all behavioral and physiological observations for a subject during the sleep onset process, we end up seeing something like this. What we would like to do is to develop a model to translate these different transitions occurring at different rates and in different directions into a single estimate of a subject's wakefulness. To do this, we have developed the wake probability model. This model estimates the wake probability, or PR wake, which is an instantaneous probability that the subject is awake at each point in time. The value in this model is knowing how a subject falls asleep, meaning the continuous change in wakefulness, as opposed to a single point in time declaring when a subject falls asleep. The time course of the wake probability represents the degree to which a subject is awake at each point in time, as well as the instantaneous probability of responding correctly to the breathing task. So a question you might be asking yourself is, why are we looking at wake probability and not sleep probability? Well, first of all, precisely defining sleep is a very difficult and open question. Sleep is a dynamic process, so trying to classify the probability of sleep would mean assessing the probability that somewhere is anywhere along this moving target. Moreover, given the literature on local sleep, we are pretty certain that both sleep and wake processes can coexist within the brain. Finally, for many practical applications, such as driver and machine operator awareness, it is more important to look at the ability to perform tasks as opposed to the degree to which someone is asleep. Frankly, it's also much simpler to make a widely accepted model of wakefulness than of sleep. To do this, we make the following assumptions. When the subject is fully awake, the wake probability is very close to 1, the behavioral response probability is high, the squeeze amplitude is high, near maximal strength, and since we've asked the subjects to keep their eyes closed from the onset of the experiment, the alpha power will be high and the delta and theta power will be low. As the subject falls asleep, the model assumes we will observe the opposite effects. The wake probability will approach 0, the behavioral response probability will decrease, the squeeze amplitude will decrease, and as alpha power decreases, delta and theta power will increase. Looking at the actual data, we see these assumptions hold true. Our objective now becomes, how do we go about fitting this wake probability model to the actual data? Well, to do this, we use something known as state space modeling. Now, while the actual mathematical derivation and theory behind state space modeling is way beyond the scope of this video, it's sufficient to know that state space modeling is a way of detecting things that you cannot observe from things that you can observe. Consider the game Marco Polo, in which someone is blindfolded and trying to find out where other people in the pool are in order to tag them out. The blindfolded person cannot see the other people, but they can call out, "Marco," and have the other people respond, "Polo." By listening to where the sounds are coming from, the person can estimate where the other people are despite not being able to see them. We call the things that can be observed the observations, and the things that cannot be observed the hidden states. In this particular example, the hidden states are the locations of the other people in the pool, and the observations are the sounds that we hear in response to calling out Marco. By creating a model of the hidden states and how they change over time, a model of the observations and how they relate to the hidden states, and the actual data that we observe, we can combine all of this information mathematically to estimate the values of the hidden states. In the case of our wake probability model, the thing we cannot observe is the probability of wakefulness. What we can observe are the behavioral and physiological observations that we can record experimentally. By mathematically defining the way in which all of these seen and unseen characteristics can combine, we now have a way of estimating wake probability. Ultimately, we want to fit mathematical models to the things we can see. Looking at the data, we can create idealized mathematical equations that replicate the shape of each of the observed metrics. For example, while they may evolve in different directions at different speeds, the response probability, alpha, theta, and delta power all evolve in a sigmoid shape. The EMG, on the other hand, decreases in an exponential function and then drops off. We use these idealized shapes as mathematical models for the way these observations change as a subject goes from wakefulness towards sleep. By combining these mathematical forms together with state space modeling techniques, we can fit all the data together to create the wake probability curve. The wake probability curve gives an estimate of the instantaneous probability of wakefulness at every point in time. At each point in time, we therefore have a full distribution of the wake probability, which provides an estimate of the level of uncertainty that we have at each time, as well as a basis for statistical comparison between and within subjects. So how well does this wake probability model work at characterizing the transition from wake to sleep? When we compare the wake probability curve with the spectrogram for the same subject, it not only matches the overall shape of the spectrogram, but also the technician's scored hypnogram. We gave this model no information on sleep stages, yet we still see a slight peak in the wake probability at the same point in time as which the technician noted a state change in the hypnogram. Overall, the spectrogram, the hypnogram, and the wake probability curve all follow the same general trends. However, rather than the sudden steps of the hypnogram, we get a continuous curve. Here's the data for a different subject. We see them awake with high alpha power and performing high behaviorally, but as they start to fall asleep, their behavioral accuracy decreases and the alpha starts to give way to delta power. However, they briefly wake up and the alpha power in the EEG comes back and they actually start performing the breathing task again. This only lasts a short time before they then fall back asleep. Just as in the previous case, we see the wake probability curve fits both the EEG spectrogram and the technician scored hypnogram, and in this case, we see that it can handle both fast and slow transitions observed during sleep onset. Now, this is all well and good when everything occurs the way we expect it to, but what happens when the behavior and physiology disagree? Here's the EEG and hypnogram for another subject where the alpha power is present, then dies out, at which point we typically consider them to be asleep. However, looking into the behavioral data, we observe that they continue to perform the behavioral tasks with high accuracy for at least another 5 or 10 minutes. What this means is that there is a disagreement between what the behavior and physiology say. This was a very surprising finding that we observed, and we found this for 2 healthy young subjects and observed this phenomena for both of their recorded nights. This suggests that there is a distinct natural variation in the way the subjects fall asleep, and we'll call that the alpha dropout phenotype. The wake probability curve integrates data from both the behavioral and the EEG observations, and as such does not simply say the subject is asleep when the alpha stops, but rather decreases the wake probability and increases the uncertainty. This uncertainty is displayed by the increase in the size of the shaded area around the curve, which represents the 95% confidence interval on the estimate. So what we have shown so far is how to take the wake probability curve and use it to describe the individual subject records. But how would we go about comparing sleep onset between different subjects? The ability to characterize the sleep onset process of groups is very useful when looking at the difference between clinical populations or the effect of drugs. However, if it takes one person 15 minutes to fall asleep, another person 20 minutes to fall asleep, and another person 30 minutes to fall asleep, in which they wake up and fall asleep and wake up and fall asleep again, how do you accurately combine the information across these subjects? With traditional methods, this has been a very difficult problem to solve. However, the wake probability allows us to do this in a very mathematically principled way. Here we have 3 different subjects, each with their own unique wake probability curve. Since the wake probability curve tells us exactly what their wake probability is at each point in time, what we can do is align them and compare the activity between them at different probabilities of wakefulness. For example, we can look at the wake probability curves every point at which they're at 5%, 10%, 95%, and so forth. By comparing the EEG activity at equal wake probabilities, we now have a means of comparing across groups. We can do this by computing the sleep onset process population spectrogram. Unlike the other spectrograms that we've seen, in which time is noted on the x-axis, this plot uses the wake probability, and we compute the average EEG spectrum across all the subjects for each value of wake probability. This allows us to provide a continuous metric for what the EEG looks like for a particular cohort at different levels of wake probability. What we see is a gradual decrease in alpha power and bandwidth, with a very gradual increase in delta and theta power and bandwidth. Moreover, what we can also do is look at particular groups of interest. For example, here's the sleep onset process population spectrogram for the subjects that exhibit the alpha dropout phenotype. We see that their wake probability is very different. In the previous population spectrogram, the alpha dropped out at a value of around 0.6 wake probability. But for this group, the alpha disappears at around 0.85. In conclusion, what we have done is to develop a framework to treat sleep onset as a continuous dynamic process. This framework integrates simultaneously recorded physiological measurements with behavioral data using a novel, minimally arousing breathing task. From here, we developed an empirical sleep onset process model based on physiologically and statistically principled frameworks. This model allows us to dynamically track the time course of the sleep onset process, finally allowing our analyses to match the observations that we see during the sleep onset process. Furthermore, it permits analysis within and across subjects, as well as the construction and comparison of subject groups of interest. Moreover, we have identified a series of subjects that exhibit an alpha dropout phenotype in which their brain is clinically asleep, yet they continue to perform a behavioral task at high levels of accuracy. With this new model to precisely track the sleep-wake transition, we can better characterize and diagnose sleep disorders and more precisely measure the effect of sleep medications. For more detailed information, please check out our 2014 paper in PLoS computational biology.